This session is on processes and capsules and how they interact so that processes can use capsule services, how they can interface to the hardware through capsules, how they share memory to get that job done. To do that, we'll talk and break this into a four-part discussion. First, focusing on the processes themselves, then how they interact with the capsules through that syscall boundary layer of going through the kernel to the capsules. How those capsules are then details about them, the types of capsules in more detail, and how those capsules interact with the hardware through the hardware interface layer and these low-level drivers. So taking a step back to the bigger picture to get a sense of what the processes are and their requirements, look at what they would be doing. And they're going to be doing things that are for an embedded system. And that brings up the question of what really is an embedded system. And when I think of embedded systems, I tend to think of things like, oh, a automated water monitoring. So for the water utility, where they can then drive by homes and automatically read the water usage without having to get out and look at gauges on water meters. So that'd be one thing. Another are these fast response real-time systems where you have, let's say, an airbag sensor and it has to fire and it has a hard requirement to make sure that it works within a very specific range immediately. Anti-lock brakes that sense immediately when tires are beginning to slip and then can pump the brakes, or sensors, embedded systems that have a just single focus of being a sensor for, let's say, temperature or some other environmental condition, or small wearable devices that people will wear, such as sensing heart rate or sensing other biological effects. Factory automation, where the devices need to be predictable and operate with other devices in synchronous. And then there's also security type systems. I think of those where you have devices that need to be able to be reliable with long battery life. And finally, non-real time, but security system related to security. So like hardware keys where you have, let's say, a encrypted or a private key stored on a hardware trust device. And so that needs to be secure from outside attacks and also be low power. So I think of these, some of the properties are real time, low power, but then think of like general purpose computers they use every day, like laptops, tablets, and phones. And it's like, well, don't they need to be real time? Like if I'm having a meeting with somebody, that needs to be real time with audio and video. And if doing gameplay, that needs to be real-time responsiveness. Also, a lot of these embedded systems deal with data, and so do general purpose computers. They also have to deal with spreadsheets, data analysis. These deal with scheduling and timing, and so do general purpose computers. Also, they need to be low power. So, like, what are the kind of the differentiators with embedded systems and laptops and general computers? Well, there's one overall theme, and that is these deal a lot with input output, very input output heavy as far as sensing something and making rapid decisions and then being able to do that in a certain time. So there's a lot of input output relationships going on there. And if we look more at those properties of embedded systems, we see some other focus properties, such as, yes, both the general purpose computing and the embedded system are real time, but if there's jitter, if there's some lag in the real time of the computer, that it's not that big of a deal where that could cause injury or accidents in a real time in an automotive situation. Also, we talk about long battery life with the phone, but that's normally like, oh, if it lasts a day, that's great. I mean, here, longevity needs to be able to last like months, years. So those, and also needs to be reliable. The systems can't crash and just go and try to reboot them. There needs to be determinism and predictability that these are very reliable systems that will produce the values that you need. And these systems are extremely resource constrained. With laptops and computers, we're talking amp hour batteries. I mean, these we're looking in microwatt type applications or milliwatt type applications. And so it's an orders of magnitude difference on that power budget. And then finally, the peripherals and I/O. The embedded systems are very I/O focused, but their I/O tends to be much slower than the general purpose computing. So, for example, with the security key, when it's using USB, it's not using the USB 4 or 3 standards. It tends to be either a low speed or full speed serial bus. So we're talking megabits versus tens of gigabits. So orders of magnitude difference on those. So these are some of the sort of differentiators to keep in mind when we look at the types of processes that are running on there. The types of processes fall under two general categories of applications and services. Applications really define the embedded system and what it's doing, while services help out those applications. So, for example, with that water utility monitoring, the service that could be a network stack that uses the application uses to send out data to a employee that would be monitoring and capturing what the water usage is. So these services do differ from capsule services, where the services for capsules are more focused on providing wrapping the hardware features such as timers and serial communication up as a service, while these services tend to be heavier services at above the physical layer and are more focused with application usage. Each of these processes, whether it's an application or service, is single threaded because, and also the Rust, the Tock operating system is single threaded. And they're also that because they're single threaded and because the operating system is a single threaded execution cycle, the process execution is sequential. So if the process is executing and a hardware timer fires, then the kernel will interrupt the process, quickly handle that hardware event, and then go back to running the process. And the process can run, can either be interrupted by the kernel after a specific time or run until the process itself decides it's at a pausing point and yields. Now, all of this, because there's can be multiple processes running and there could be yielded at times, needed to be restarted, that the processes are tracked by a process ID structure internally with Tock. And some of those details are interesting to see to look at how Rust is used in the Tock operating system. So the process ID structure has some interesting properties and functions to look at. One of the first is that it has a copy trait. And the copy trait, a lot of times see with primitives like integers or floating point numbers, things that are as easy to copy as to borrow. It's also good to prevent have to deal with long-lived borrow. So if something needs to borrow a structure for a long time, it can be easier to just copy those. And so because the structure doesn't have a lot of take up a lot of memory, it's just as easy to make copies of these tokens. Another interesting part is how you get a valid handle for it. So one thing, even though the structure is public, these two data elements are restricted to with public crate to locally within that crate's code that are the only ones that can access this. So this helps to hide the data usage, and then also allows, when combined with the like the public crate index, to be able to restrict who can get process ID numbers. And another common usage with Rust is the usage of option and result, and so this forces errors to be handled so that if the process ID isn't valid, special code has to be done by the calling function to handle that. Another issue is how to restrict access to just the process ID structure, and you can use unsafe with because the kernel code can use unsafe, so that's a way to protect to use as a form of access control, since only the kernel code capsules aren't allowed to use unsafe. Only the kernel code can use unsafe, so that this is a way to restrict access to code that you can trust. But one of the problems with unsafe is that it's not very fine grained. And so these traits that are passed in are a way to show that the calling function has access to be able to use the new external, because these are unsafe traits. And we'll talk about those more later, but it's a way to also manage the access control to these process ID structures. Returning back to the process itself, so there's some interesting properties of the user process. One, again, is that there's no language restriction. The processes can be written in whatever language, so with whatever safety or not. The safety here is performed by the microprocessor hardware, microcontroller hardware, that these regions in memory for the process are fixed, and that they're maintained by a hardware memory controller. Um, so that hardware controller restricts the process from being able to access hardware registers on the microcontroller. So it can't access the hardware directly. It has to go through the kernel to access the kernel, or the capsules, which can do that. Also, these processes, they have their standard heap, so you could have dynamic memory allocation. You have your data and then the stack. They have this grant space, which I'll talk about in a second. But what they can't do is talk to other processes. So they have to use some form of inter-process communication to be able to talk to those. So that helps to protect processes from each other. The processes are protected, or the kernel's protected from the processes through the hardware memory controller, and then that also protects the processes from each other by having defined memory space. This grant region is special, I think, with Tock, in that it solves the problem of what happens if you have a process that wants to use a lot of kernel resources. So, for example, if a process wanted to use a bunch of processes wanted to use the UART, or a process wanted to use, let's say, a lot of the capsules, that could exhaust memory in the kernel if the buffers for those are being maintained by the capsules at the kernel layer. So instead, those data structures are maintained by the process they're maintained in the process memory by the kernel through the use of the grant region. So the process can't access this grant region, only the capsule code and kernel can, but it serves as a way to then protect the kernel if, for example, let's say they're used up a lot of memory. If the process is run out of memory, it only takes down the process and doesn't cause problems with the kernel. So we talked about that, and if we look now at who chooses which process to run, that brings up the big issue of scheduling. So there's a couple different types of scheduling. One is cooperative and the other is preemptive scheduling. The nice thing about cooperative scheduling is it really simplifies the reasoning about who's running, because everybody just runs until they're done and then they allow the next process or the kernel or the capsule to run. And so this avoids, if everybody can be trusted, this avoids, the kernel avoids locking and synchronization issues. And you can just use a event loop. And you can trust that the tasks will run to completion before yielding control. So they'll, when they get to a state where they need to wait on IO or some other timer, they can then yield, and that you can trust them. This trust is implied in the capsule code. So the capsule code does run cooperatively with the kernel, that it runs atomically with respect to the other capsules. Capsule code can hang the kernel, so there's a trust there. A lot of times, preemptive scheduling for processes is used, and that's to prevent one process from hogging all the CPU cycles from the other processes or from capsules, and that's really important for a responsive embedded system where you have um, times that need to be near real time. And with that, Tock has a round robin scheduler. And so this just schedules to make sure each process gets its turn with the CPU slice. And the kernel then will preempt the process that runs too long or gets or stalls out. The cost is now the kernel's having to do preemptive calls. And so that raises some inefficiencies. And finally, we have the capsule versus process scheduling. So in either of these cases, the capsules run atomically and they're not preempted by other kernel tasks. So the scheduling applies to the processes, not the capsules. The processes can be preempted using the preempted scheduling. And there can be, but the downside of that is that context switching of running different processes preemptively, you have the overhead, and that slows things down. So this brings up for a design approach that when designing the implementation of an embedded system, that any simple or latency sensitive tasks that need to be responsive can implement as capsules, but then kind of like network stacks, like these larger tasks or less trusted tasks that implement as processes for better isolation. The scheduling is tracked by a number of different user process states. So these apply to the process and not to things like the kernel. The different states, and we'll compare them to Linux, are the running state. And this just means that it's ready to run, but it's not necessarily running. Just because a process is in the running state doesn't mean it's actually running. The process could also be in the yielded state, which is similar to the Linux block state. And that is the process is waiting for an event. So it gave up control. It's waiting to have something done, timer to fire, and it's not ready to execute. And so it's a lot of times that will happen when the process intentionally calls the yield system call. And then the process can be rescheduled to run again. There's also stopped running. This would be similar to terminate in Linux. and that it's done and it won't be scheduled again by the scheduler unless you manually resume it. So to put it back in a running state. And another one is stop yielded. So this again this one's similar to Linux terminated, like stop running. It's just that in this case, it was stopped while it was in the yielded state, and that it would have to be scheduled again, would have to be put back in the yielded state. Both of these are normally stopped by a driver. So the process control is where you can, that's a capsule that allowed you to be able to stop the processes and have some fine-grained control over things. A couple other ones are faulted. That's similar to the Linux either terminated or faulted, and that's when the process generated some fault, normally a memory access issue. Um, and then there's the terminated. So in this case, that's just like the Linux terminated. And the process is intentionally executed the exit terminate system call. So it's saying it's done. Did what it needed to do. It's not yielding or waiting. It's just done. And this is also, there's an unstarted, which is like new. So it hasn't yet started anything. So Linux has a running state, but Tock doesn't, because Tock is single threaded. So the process couldn't be running while the kernel is actually running. So that state doesn't exist. Now, if we look, we've talked about scheduling and looked at the states. Just to look a little more at the details on the schedulers. So the round robin scheduling with the preemptive scheduling, that one is called round robin sched. And you can look that up in the Tock code. That's the name of it. And what that does is that just preempts. So the kernel will preempt a process. Here we have three processes, A, B, and C, and so they're running. They each get fixed time, and then they just repeat. So it just makes sure everybody has a fixed amount of time and bases fairness on that. The other schedulers, that cooperative scheduler that we talked about, and in this case, instead of the kernel preempting the processes, we have these three processes, and the processes yield control back to the kernel. So there's trust there that it'll yield control, but it's more efficient. You don't have a bunch of operating system calls there, just the ones when the yield is necessary. And then there's a priority scheduler. So in this case, the task can be scheduled. You can do it by preference, and then that gives predictable latency for the tasks. And this priority scheduler is done with a process task list, and so it just keeps scheduling until the one in the list is done, and then it will move on. There's another one called a multi-level feedback queue scheduler. Talk about that one in another presentation. It's a little more complicated. But to look at some specific Tock code, here we have some of the specific code for scheduling. So a couple of the traits. So the scheduling code is located in scheduler RS, and the scheduling trait and scheduling decision are two interesting bits of type to look at. And so you can see that also the scheduling timer is used in the process, so that trait, and this one's necessary if there's going to be preemption of the code. And the way, this is just a couple snapshots from the code, but the way the scheduler and the scheduler types are kind of tied together to the actual hardware is through these namespaces. So being able to make a shortcut defined scheduler type that's now based on this is the NRF 52840, which we'll be using some of the board examples for. So This way you can tie the scheduler to a specific scheduler on for a board, and then also to specific chip hardware. So for like the scheduler timer, which is going to need to be able to use specific hardware that's platform dependent and processor dependent, can be able to tie these to there, but then just use the scheduler type and scheduler timer type to keep everything generic.